So I happened to find this question in one of Mr. Matindih's lecture notes. So the question reads, prove by mathematical induction that 1 plus 3 plus 5 plus dot dot plus 2n minus 1 equal n squared. So we prove by mathematical induction. So proving a mathematical induction question, we basically look at 3 steps, just 3 steps, and you're done. 3 steps. So let's begin. So we say let P of n such that 1 plus 3 plus 5 plus dot dot plus 2n minus 1 equal to n squared. Okay, so I said there are basically 3 steps in proving a mathematical induction question. So the first step is to say for n equal to 1. So I am taking it slow so that you people can understand. Yes, so for n equal to 1, p of 1 is such that, so if you say you take that one, this one, we put it here. Okay, we put it here where there's n, we put 1 here. So we'll say 2 multiplied by 1, then we subtract 1. We see that we are going to get 1 if we subtract 2 minus 1, okay, which is basically equal to 1 raised to power 2, because 1 raised to power 2 is basically 1. Okay. Now we have seen that this is equal. So this is the first step. So we prove that it is true. So we have seen that it is true. This part is equal to this. Now for the second step. So for my second step, I'll say let's assume P of k is true. Okay, so P of k is true. That is okay, so P of k is such that we are going to get what we have here. So 1 plus 3 plus 5 plus dot dot plus 2. Now where there is this n, we'll put k. Okay, so we'll put k, then we say minus 1 equal k squared. Even where there is this n, we put k as well. So that is our assumption. We assume. So in our step 3, we use the assumption in step 2. So we use the assumption in step 2 to prove that P of k plus 1 is also true. So we use the assumption in 2 to prove that P of k plus 1 is also true. So P of k plus 1 is also true. So it implies that P of k plus 1 is such that 1 plus 3 plus 5 plus dot dot plus 2k minus 1, which is basically this. Okay, then where there is this k, the next term, we are going to put k plus 1. Okay, where there is that k, so we'll say 2 open brackets k plus 1, then minus 1. So this is equal to k plus 1. Where there is this k, we put k plus 1, then we square it. Okay, we square it. So now our proof, to end our proof, is basically to show that this part here, okay, what we have here is equal to this part. That is how we end our proof. So let's see now. We show that this part, okay, which is our left hand side, should be equal to the right hand side. So is it possible? Yes, it is possible. We can show that. Okay, to prove now, I'll say for left hand side we have this part, okay, which is basically this, what we have here, which is just this. This is our left hand side. So we show that this left hand side is equal to this right hand side. So we write this. Now we see something here. There's something which is similar somewhere. Okay, you can see that what you have here, which is 1 plus 3 plus 5 plus dot 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 plus 2k minus 1, is basically what you have here, where you assumed p of k is such that this is equal to k squared. Now you can see that this part is what you have here, and you are saying it is equal to k squared. So which means this part we can replace it with k squared. So it's k squared, then plus we'll add this, what we have, we are saying plus this, so we'll add it. Okay, so we have added, open brackets 2, open bracket, k plus 1 minus 1, which is just basically this part. Okay, we haven't done anything, we haven't changed anything. It's basically this. Now if we try to expand this, let's try to expand this. So expanding that one, oh sorry, here, sorry, this is k, so it is 2 multiplied by k, then plus 1, which is basically 2k plus 2 minus 1. So simplifying it, we get k squared plus 2k plus 1. Then if you try to use if you solve this one by factorizing it, you will basically get k plus 1 raised to power 2, which is identical, okay, identical to the right hand side. So hence you have shown that the left hand side, which is this, this is equal to your right hand side. Then the next one, the one that finishes this proof, is to prove that this right hand side is equal to your left hand side. So to our right hand side we have k plus 1 squared, which we have here, okay, k plus 1 squared. So we show that this is equal to this. Is it possible? Yes, we can show that. So let's see. So expanding this, we get, so this k raised to power 2, which is k squared, then k times positive 1, which is k, then multiplied by 2, we get 2k, then you have this one raised to power 2, which is basically 1, so you have expanded that one. Okay, now you can see that this part, the k squared, is basically what you had here. You said p of k is such that it is this, okay, which is basically equal to k squared. So the k squared is basically this, what you have here. So where there is this k squared, we can replace with this, what we have here. So the k squared basically becomes this, okay, the k squared basically becomes this. Then we add plus 2k plus 1. Okay, so plus 2k plus 1. So I haven't changed anything. It's basically what you have here. Okay. Now if you look at the plus 2k plus 1, it's what you had here. It's basically this. Okay, basically this. So to resolve this part, I've basically introduced a 2, so which means I've done basically nothing. I've added the 2 and subtracted the 2, then plus 1. So if you say positive 2 minus 2, you basically get 0. So it will lead you to this same thing. Okay, so in this case, I'm going to factor out the 2 here. I'll factor out the 2. We see what we can get. So if we factor out the 2, we get, so factoring out the 2, we put the 2 there, we will have k plus 1. And resolving this one, we have minus 2 plus 1, which is minus 1. Now you can see that this, what we have here, it's basically what we had here. Okay, which is this. So you can see that this is identical to the left hand side. So hence we have proved the mathematical induction. We have proved the mathematical induction that P of k plus 1 is equal, is also true. Okay, so P of k plus 1 is also true. So we have shown the mathematical induction. So this is where you end the mathematical induction. You just conclude. So therefore, P of n is true for all n. Then you end your mathematical induction proof. So it has been Moses. Okay, so see you next time. Have a blessed day. Thank you for tuning in to my YouTube channel.